Hello, and welcome to Aggressive Physics. Today is day 111. And what I'd like to do today is simply solve some sample problems. We've been talking about a lot of different equations, and I think today is a good opportunity for us to see how different the electric field and the electric potential are. And what I like to do is solve a fairly complex problem when we're dealing with electric fields that turns into a much easier problem when we're dealing with electric potential. Remember, the electric field is a vector quantity, and we have to worry about vector addition. On the other hand, the electric potential is a scalar, so it would be a lot easier to calculate the electric potential at any point in space because you don't have to worry about the direction of the forces like you would in the electric field, or the direction of the field as we would in the electric field. So what I'd actually like to do is solve the same configuration of charges in a square pattern. Solve it first using the electric field, and then solve it again using the electric potential. And you'll see that the electric potential is much easier to deal with. So if given the choice, always use the electric potential rather than the electric field to solve for problems, because you don't have to worry about vector addition. So let's take out the whiteboard now and solve some practice problems dealing with electric potential versus the electric field. Thank you. All right, the electric potential has a different version of its equation other than the W over Q. Now that's our standard, and that's the level of introductory physics for electric potential. But we often have this other version, which is KQ over R, that we could also use to find the electric potential. And what would be important about this is that would be the potential at a single point, but you need 2 points in order to find the potential difference, which is truly the important term. Now this looks very similar to the electric field equation, which is KQ over R squared. So first of all, there's only one R, not the squared. And second of all, you'll notice I put the vector symbol on the E, but the V, the electric potential, is just a scalar. So we have a scalar versus a vector. And armed with these two equations, we'll find that some really complex problems can be solved quite easily. What I'm going to do is the same problem, I'll find the electric field, and then I'll find the electric potential at the center of a square with 4 charges on the outside of the square. Okay, what we're going to do is a sample problem, and we're going to find the electric field at point X, and we're going to find the electric potential at point X. Now, all of these, this proton, electron, and proton, are the same distance away from X. So the R value is going to be 2 angstroms. Now let me tell you what an angstrom is. An angstrom is 1 times 10 to the negative 10 meters. So the angstrom is not only a prefix, it's also a unit. So it represents 1 times 10 to the negative 10. So this would be 2 times 10 to the negative 10 meters. And all 3 of them have the same value, so I'll just leave it at that. Now, in order to find the electric field, what we're going to do is KQ over R squared. So 9 times 10 to the 9, Newton meter squared over Coulomb squared, times, they all have the same general charge, 1.6 to the negative 19 coulombs, all over 2 times 10 to the negative 10 meters squared. So let's find the value for that. 9E9 times 1.6 E negative 19 divided by 2E negative 10 squared. And I'm getting 3.6 times 10 to the 10 newtons per coulomb. So that's the electric field caused by each of these objects at point X. Now, if we just look at point X, what would a proton do? Well, a proton will be pushed by this proton this way. a proton will be pulled by the electron this way, and a proton will be pushed upward by that other proton at the bottom. So we'd have two 3.6s times 10 to the 10 newtons per coulomb going to the right and one going up. And what that's going to do is create a right triangle. And that's going to be 7.2 times 10 to the 10 newtons per coulomb and 3.6 times 10 to the 10 newtons per coulomb. So if we draw it tip to tail, what we need to do is use Pythagorean Theorem and inverse tan. So this is going to be a vector problem at this point. So the electric field is going to be pushed by the two protons and pulled by the electron. So let's find the total answer. 3.6 times 10 to the 10 is already in my calculator. I'm going to square that. I'm going to add it to 7.2 to the 10, which I'm also going to square. And then I'm going to take the square root of that. So I'm going to get 8 times 10 to the 10 newtons per coulomb. That's the hypotenuse. But I also need the angle. So inverse tan, opposite, is 3.6 to the 10 divided by 7.2 to the 10. And I'm going to do second tan. Where is it? Tan. Second answer. I am in radians. Let me get into degrees. Clear. Second tan. Second answer. I'm getting 25 degrees. So my final answer for E is 8 times 10 to the 10 newtons per coulomb at 25 degrees. And since I don't have north, south, east, or west, I'm just going to say 25 degrees, assuming that I'm on an XY coordinate system. So quite complex when dealing with the electric field. Now let's look at the same problem using electric potential. So let me reset the board and we'll find the electric potential. So we're done with this part. Now the new equation we have for electric potential is KQ over R. And all of these have the same value for Q. All of them have the same value for K, 9 times 10 to the 9, Newton meter squared over Coulomb squared. 1.6 times 10 to the negative 19. And R is 2 times 10 to the negative 10 meters. No squared. So 99 times 1.6 e negative 19 divided by 2e negative 10. And I'm getting 7.2 volts. Now, since each has the same value, what I do, and it's a scalar, I'm going to say plus 7.2 for this proton, minus 7.2 for the electron, volts, and plus 7.2 volts for the proton. So plus 7.2 minus 7.2, those cancel, and I'm left with 7.2 volts. Scalars don't need vector symbols. Scalars don't need Pythagorean theorem or tangent or inverse tangent or anything like that. In fact, if I realized that the proton and electron were there originally and they were the same values, I could have canceled them out before I even started and realized that only one extra proton would have produced the electric potential at that point. So my answer is simply 7.2 volts. A lot easier than dealing with the electric field, which took us much more time and a lot more in terms of calculations. So when in doubt, use a scalar quantity if given a choice. If you have to do a vector quantity, you have more work to do.